right, everyone, so it's time to begin. And so after this class, we only have 3 classes left. And the last class is going to be a review for the final. So we really only have this class left where we're going to talk about the 2 sample Z test. And then 2 more classes where we're going to talk about the chi-square, 2 different types of chi-square tests. And then the last class will review everything. Now I want to remind everybody that the final is cumulative. And unfortunately, I can't give you the same flexibility of taking either final that you want. Like, you know, the final schedule is what? If we go to, let's just go to calendar here. Okay, so your final is Tuesday. No. Yeah, yours is 7 to 10. If you're in this class, it's Tuesday, 7 to 10. If you have 3 finals in a row, you can take this conflict final. Actually, this final is more open. If you really want to take the later one, you probably can. And all you have to do is come see us in 113 Illini Hall, and we'll switch you over. What's happened is the university won't give me any more space for this final. This final is jammed up. And so I can't let you switch from this direction to this. I just can't get any more space. But I can let people, if they want to switch from here to here, they can. Now, the rule is that if you're not allowed to have more than 2 consecutive finals. You can't have 3 finals in a row. So under those conditions, if this final right here, if you have, let's say you have a final Friday night, you have this final, and then you had a final Thursday night. Well, then one of the 3 of us has to give you, one of your 3 classes has to give you a final, a conflict. And I could do that. I have enough space that I could put you in Tuesday here, if your other teachers can't. So yeah, if you have 3 consecutive finals in a row, so you have one, the only other way that could happen is what? If you had one in the Thursday afternoon, Thursday night, Friday morning, and Friday afternoon, that's one, or Friday morning, afternoon, and evening. So if you have all 3 on Friday, or if they start Thursday and continue through, then you can get a final, a conflict final. But if you want a conflict final switching this way, we can probably accommodate you. Just come to the lab. Any questions on that? All right, now your grades. I'm going to get your grades in order so that you can see on Compass what you need to get, what score you need to get on the final to achieve whatever grade you're aiming for. So, you know, it's going to be an estimate because not all the homework's in, but all the exams are in, and you know how much bonus is left. We'll tell you how much bonus you have, and I'll post a formula so you can anticipate what you need to get on the final to achieve whatever grade you're aiming for. So I'll get that up this weekend. All right. Now, what do we have left? We have a homework due. Where are we? Right here. So we have 1, 2, 3, 4 more homeworks. You'll have to anticipate what you'd get on those. And we have 1 more bonus survey. And then we have a bunch of iClicker questions. Now with the iClickers, you're allowed 3 free days. They total to 56, and you can only accumulate 50. So you can drop 3 times. Your 3 lowest scores will be dropped. And all this is explained, because some people don't know where to look for the grades. All of this is explained under these tabs. You can go to you can go to the syllabus and it'll explain everything. And explains how everything's figured out. And if you want more detail on any one of them, you go to the bonus or homework, etc. So this is where you go for all the information. Questions? All right. Well, now let's go back to the document camera here. And we're on chapter 245 on the two-sample z-test. Okay, so what we've been doing so far is we've been looking at a one-sample z-test. We have one sample, and the null hypothesis is always that whatever effect we see in that one sample is just due to chance. It's a null hypothesis. Nothing interesting is going on. And it's usually the alternative hypothesis that we want to prove that says, no, this effect we see is not due to chance. It's due to some particular cause. Now, and we're comparing one sample to a model, a box model based on a random draw. Now, we're going to look at two samples, which happens much more often. Let's say we wanted to compare differences between males and females. Are they small on some performance test? Are they small enough they could just be due to the luck of the draw and males and females are really equal on this? Or is that difference too big that it's unlikely to be due to chance? Or more commonly, we're going to be comparing treatment and control groups. Like, did the drug work? You see some effect. The people who took the drug looked like they're in better shape than the people who didn't, but is it a big enough chance effect that we can say it wasn't just due to the luck of the draw? All right, so that's the idea. So, and it's going to be done very, very similarly. All right, so in chapter 20, we tested hypotheses about population averages or percents using this statistic, observed minus expected over the standard error, right? This is the difference we see, some difference, and we don't know if it's big or small until we compare it to a standard error. Or we use the t-test when we had a small sample size. But now we'll try to test hypotheses that compare the averages or percents of two populations. If our samples from these two populations are independent, that means sampling from one doesn't change what we'll get from the other one, then we use the test statistic, this very similar one. The difference we observe in the two samples, minus what we'd expect under the null, which is always 0. The null is always, hey, there's no difference between men and women, let's say, no difference. We just happen to see a difference between men and women in our sample. Let's say men and women's math skills or something. There's no difference. We'd expect no difference. We believe they're really equal, but yeah, in our sample we see some difference. And we think that's just due to chance variation. So this is always 0, the expected difference. And then we have to figure out some standard error that takes into account, there's a standard error for the difference. It takes into account the variability that's coming from both the men and the women. So if our null hypothesis is that the two population averages or percents are equal, which it just about always is, then the expected difference is 0. That's 0. So this is our test statistic, just the difference you see, for example, between men and women, over what we typically see if there was no difference. If there was no difference and we just, by the luck of the draw, we're going to have some difference, we're not going to get exactly, they're different people, what we'd see just based on the variability inside that men and women have, just the variability within each sample group. Okay, so how do you compute the standard error for difference? That's the only thing that we have to figure out. How do we do that? All right, well, maybe I should clarify here that this expected difference is always 0 in all the problems we're going to look at. It's always 0 because the null hypothesis is always that there is no difference between the two groups. It's always that there is no difference between the two populations. We just happen to see in our little sample a difference. Okay, so it boils down to this. Since this is 0, it's really easy. It's just the difference we see over the standard error for difference, okay? So how do you compute this standard error for difference? That's the only new thing here. Let me just give you an, yeah? Good. Okay, so how do you compute the standard error for difference? Let me just tell you in general, okay? Let's say you had 2 samples. You had a sample A and you have a sample B. And sample A from an A population, sample B from some B population. And let's say you get an average here of your sample, I'm just giving you a real general, of 100, and let's say your average here is only 90. And then you're going to have to get a standard deviation. So there are not only hundreds inside this A box, there's lots of different numbers, and let's say the standard deviation, the standard error for the average, how much this bounced around, is 4. I'm just making these numbers up, and let's say this one is 3. Okay? Now this is what's the standard error? How do we combine these two is the question. What are we even doing here? Well, when we look at the difference between A and B, the difference is what? We're looking at the difference between these 2 averages. It's 10. But the difference is going to be what? 100. It's not always going to be 100. It's 100 plus or minus 4 on the average. That's what you'll get from A. And then you'll subtract off what you'd get from B, which is 90. And you're not always going to get 90. Plus or minus 3. So the difference is 100 minus 90, which is 10, yeah? And what the standard error for the difference is 10 give or take what? How do we combine these two? Should we say 10 give or take 7? Just add them? Should we say 10 give or take 1? Just subtract them? Let's think about it. We know there's uncertainty here and there's uncertainty here. So when you're sampling from both of them, you're bound to have more uncertainty than you would if you just sampled from one of them, because you're adding some uncertainty here. But since it's plus or minus, they could cancel out. For example, if you think it's 7, how would we get 7? You'd have to get a plus 4, 104 here, that difference, and then you'd have to get really low here at negative 3. So you'd get a minus negative 3. That would give you 4 plus 7. And if you wanted negative 7, you'd have to get 100 minus 4 here, and then minus plus 3. So that would give you the biggest difference you could get, but often you're going to get like a plus 4 here and a plus 3 here, and then you'd have 4 minus 3 is 1. So what I'm saying is, you know that it's going to be bigger. You're going to, since there's 2 sources of uncertainty, you know it's going to be bigger than 4, bigger than either one of them, bigger than 3 or bigger than 4. But you know it has to be smaller than the 2 of them summed together because the signs could cancel out. And basically, the way we figure it is, that's sort of the intuitive reasoning. And the idea is that the standard, you take the standard error of the difference is basically this Pythagorean theorem. It would be the square root of 4 squared, the error from this one, plus 3 squared, which is 5. Think of it as the Pythagorean theorem, okay? So you get 4, you get an error of 4 from this one, and an error of 3 from the other, and this is 4, and this is 3, and the biggest error if they would be 7, but really, the way that we combine them is by the hypotenuse of that triangle, which is 5. So you know that going from here to here, it's much shorter to go this way than to go all the way around. It's smaller than the two added together, but obviously it's the longest side of the triangle. It's bigger than 4 and bigger than 3. So that's a way you can remember it. Okay? So they sum as the square root of the sum of their squares. And if you want to see a mathematical proof of that, I can post that on our website. Okay, sounds good? Or if you could, you don't want to see it now, probably. I'll just post it on the website. Okay. Now, so now if the samples are dependent, it doesn't apply. What does that mean? That means that if I sampled a -4 from here, let's say, then that would affect what happened here. I say, oh, you got a negative here, then I'll give you a positive here. Like they'd be the opposite or something. Then in which case you'd get bigger standard errors. Or if I gave you the same size sign, you'd give smaller. So you don't, whatever you draw from here doesn't affect this one. That means these formulas apply only if they're independent. Okay? Questions? All right. Okay, let's decide which problem we want to do. We could do this problem, let's see. We can do this problem. This problem was once very exciting to people. Back when I taught in 2003 and 2004, this Atkins diet was an extremely popular diet. It was a very high protein, high fat diet. And it was making headlines everywhere. And so I was very excited when I saw that in the New England Journal of Medicine, a very reputable journal, that they published a randomized trial comparing this diet, this Atkins, this high protein, high fat diet, to the more conventional high carb, low fat diet that, you know, people had talked about for years. And usually, this is the first time I'd seen this. I was really excited. I mean, these diets have been around for years. This Atkins diet, I remember it when I was like 12 years old. It was called the Stillman diet, when a whole bunch of my friends were going on it then and just eating meat. And then they just repackage it, and all of a sudden it's called a different name. They just go in cycles. And usually, the evidence for one or the other are just testimonials, anecdotal evidence. You'll see some fat person like Kirstie Alley or somebody, and then she loses a whole bunch of weight, and she gets paid for Jenny Craig until she gains it back, and then they fire her, and then they'll put another fat person who loses a whole bunch of weight. Jennifer Hudson still looks good, but you see these people up there, and they just, you know, they come on as blimps, and then they just lose, and then they, it's just, that's anecdotal evidence, just because it worked for that person, and you can't really trust it because, you know, anybody, you know, they can do shots that make the people look much thinner too. So this was amazing. I said, wow, this is just what we do in Stat 100. Let's see how it came out. So here's how they did it. The subjects were 63 obese men and women. 33 were randomly assigned to Atkins, and 30 were randomly assigned to the conventional low-fat diet. And now, let's forget this sentence for a minute. After 3 months, the Atkins group lost an average of 6.8% of their body weight. Well, let me get a highlighter. So this is how much they lost. Well, the low-calorie group lost 2.7%. So they used percentage because the more you weigh, if you weigh, you know, 200 pounds, a 5-pound difference isn't nearly as significant as if you weigh 100 pounds, a 5-pound difference. So like, you know, for a 200-pound person, 6.8% would be what? 13.6 pounds, right? and 2.7 would be 5.4 pounds. So that looks like a huge difference, doesn't it? All right. Could this difference in weight loss be due to chance, or did the Atkins diet really work better than the low-cal diet? Set up a box model and state the null and alternative hypothesis. All right. Well, there's lots of different ways we can set this up. But the math works out the same for all of them. So I'm going to give you the one that's easiest to do mathematically. And that is, assume the people are chosen from a population of thousands of people wanting to lose weight. There certainly are thousands of people wanting to lose weight. So we have this idea where you have this thousands of people. And you imagine, because we're not just interested in this group, whether they, I mean, it's not like we're not interested in them, but we want to know if that diet would work for me and you, if we were interested in losing weight. So imagine just thousands or millions of tickets, we can say thousands of people. But we don't have, it's very expensive to do these experiments. They monitor these people very, very carefully and keep track of exactly what they eat. So they can't cheat, and it's extremely expensive to do it on thousands. So instead, they pick, out of those thousands of people, they pick 63 people, okay, to be out of them. And they pick 33, so there's thousands of tickets. Let's call one of them the Atkins box, and the other one we'll just call the low calorie, the conventional. Okay, this is the new one and this is the old one. And imagine, what you have to imagine is that all the thousands of people who really, really wanted to be in this experiment were. And on each ticket, they'd have thousands of tickets in here, is how much weight they would have lost if they were on this diet and how much weight. But we really only you only picked out of these n equals what? 33 for this group. And without replacement, we wanted separate people. And here we only picked what? 30 without replacement. Now, and inside there's lots. And with the 30, their average was what? Loss was what? 6.8% of their weight. And here they didn't lose as much. This was only 2.7% of their weight. Okay, but what's inside here? There's thousands of tickets. On each is written a weight loss, what they would have lost if they went on this diet, okay? So this is their average and a standard deviation here, and this is an average and a standard deviation here. On each is written a weight loss. Now is this percent, do we even have to, is this a percent problem? Why do I have an average here? I have percents down here. I say that I want on each ticket how much weight, a number, how much weight they lost. So why do I even have a percent here? This is just a label. This does not mean, you can cross it off if you want, if it's confusing. It doesn't mean that 6.8% of the people lost weight, ones and zeros. No, it's just a percent of their former weight. So it's just, you can just think of it as a number, 6.8. And we want the average of all. Some people lost 0%. Some people lost 20%, and they averaged them all and got 6.8%. So you understand how, don't get confused by it being a percent, right? We have an average problem here. Do you understand? Do you get it? Okay. So now, and what was their standard deviation? We were given that. That was 5. I'm going to forget the percent. And here the standard deviation was 3.7. All right. Now, what does the null say? The null says, okay, yeah, you got more weight loss from this Atkins than you did from that. You only have 33 people here. If you took a different 33 people, you might get less weight loss, and if you took a different 30 people from here, you might get more. What I'm telling you is these diets don't work. They're the same. That's what the null says. If you He tested a couple of people. These people probably, just by the luck of the draw, happen to be people who lose weight more easily. And here, you just by the luck of the draw, you chose people who weren't as successful. You know, this difference is not enough of a difference that you can say it's not due to the luck of the draw. In fact, why don't we just assume they are equal, that these boxes are completely equal, and we'll see how likely it is to get this kind of a difference when you have equal boxes, like just when neither diet works. I'll show you that that's a small difference, and just due to the luck of the draw, and we'll call that our p-value, and it's got to be more than 5%. That's what the null says. Okay? And the alternative, so let's write that down. So the null says, the null is always what? That these two boxes are equal. What do I mean by that? That the average in Atkins is equal to the average in locale. They're equal. And these differences we see are just due to the luck of the draw. That's the null. Now what's the alternative say? The alternative says no. This is strong, this difference here is strong evidence that the Atkins works. We wouldn't see a difference like this. We would not see a difference this big of what? 4.1 difference like this, 6.8 minus, if these two were equal, that just would not happen. That would be so unlikely. So the alternative is the Atkins really, the reason we're seeing this bigger average is because the average in the Atkins is what? In the whole box, truly is bigger. They do lose more weight than the average in the locale. So that's the idea. Do you get it? And from here, it's pretty easy. And then after we go through all this, I can explain to you, maybe if you're interested, a different way we could have set it up that's more intuitive, but the math is harder. And it works out to be the same thing. But let's go through the math first here. All right, so questions so far. Now, what do we want to do? Well, time to compute our test statistic. So far, we've learned the one sample Z and the one sample T. Those are both test statistics. Now, do we want a Z or a T? I'm going to go with, what's our sample size? I'm going to go with the Z because our sample size is big enough. Remember, we decided we were going to cut it off at 25. If we had only less than 25 in each of these, I'd go with the T, the two sample T. But now I'm going to do the two sample Z. And so leave some space here because we are going to have to compute a standard error for the average for both of these. But let's see why. Let's go down to here and let's see. Now we want to compute our test statistic Z and then P. All right, first Z. What is Z? Well, Z is just going to be our observed difference. Should I say minus the expected or not? I'll do it this first time, but then we won't do it because the expected is always 0. This is just 0, that there's no difference. So it's just our observed difference. This is 0. Our observed difference over what? Over what? Do you think this standard error, that standard error? It has to be a standard error for the difference because both of them are bouncing around. Okay? So what is our observed difference? That's just the difference in our averages, which is 6.8 from one box minus what from the other? Just this. This is the claim, that this difference is big enough that means the Atkins worked. Well, what is that difference? That's 4.1, but is that big or small? We do not know until we see how many standard errors it is. Remember where we're headed. We're headed to this, right here, where there's our value, z. And our expected is also, gosh, I didn't leave enough room. That says a z, but our expected is also 0. And we want to know where to put 4.1 on here. Where? Is 4.1 just a little everyday occurrence or not? This is easy. We just have to, once we figure out what our standard error is, how many pounds weight loss is our, what's one standard error? Well, then we'll see if it's big or small. So we got to get this to get our z. Okay, so this, remember, is what? This equals, I can stick it right here. It's going to be, like the Pythagorean theorem, it's going to be the standard error from 1 squared plus the standard error from this other squared. And those are both going to be standard errors for the average from each sample. Okay, that's what we're going to put in here. That's why I said to leave room. Don't put the standard deviations in here. We're talking about averages here, so we've got to get the standard error for the average. So what's this standard error for the average? It's SD divided by what? Divided by what? Yeah, square root of n. So that's SD is 5, divided by n is what here? 33. So I got 0.87. That's what goes in here. Okay? And now how do you do this one? We take SD, 3.7, divided by the square root of what this time? 30. Does everybody see that? Questions? So this is 0.68, and that's what goes in here. Okay? Questions so far? All right, now what do we want to do? What we anticipate is going to be a number bigger than either one of these, but smaller than their sum together, just like the Pythagorean theorem, right? That was 0.87, and that was 0.68. We want this hypotenuse here. So it's going to be bigger than either one of them, but smaller than their sum. And I got 1.1 when I did it. And that certainly fits the bill. The 1.1 is bigger than 0.87, bigger than that, but it's smaller than the two added together. So it looks right. And then when I do this, I got 4.1. So that's one standard error. So we want to know how many 4.1 is, and it turns out to be 3.7 standard errors. That's our z-score. Now you look at that, and do you think it's going to be way, don't you know it's going to be way at the end of the curve? That's going to be highly significant. If we look up 3.7 in the back of the book, we get 99.978 in the middle, which means this is just going, this diet was extremely successful. So this right here is 3.7, between 3.7, I'm sorry, so messy, and negative 3.7, we have 99.978 of the area. So we have a spec here. That's the probability that if the diets really were just the same, worked equally well, there's no difference, that we'd see this just by chance. And that's our p-value. And in this case, p is unbelievably small. It's 100 minus that divided by 2. So it's what? 0. What is it? 11, right? 22 divided by 11, right? Okay. So it's 0.011. So, and that's where, this is where 3.7 is, or if we wanted to look at the diet, it's where this difference of 4.1 is. I can't even write it there. 4.1 in terms of a diet number. Anyway, let's put our conclusion here. Conclusion, because it's so hard to see. P is tiny, 0.011%. So we reject the null, that it was just due to chance, and we call it highly significant results, and have very strong evidence, have highly significant results, because that comes in at 0.1. At 1%. Look at this. 1%. Look at this, is ridiculous. We reject null and have highly significant results. Extremely strong evidence that the diet works. For the Atkins diet. Okay. I feel in case people are interested in dieting, I should say something else about this. Reading the literature on this, it looked like it was a good study in that, not only on terms of losing weight, but in terms of cholesterol measurements and everything else, it was a helpful diet. The only thing is, though, that after a while, this was after how many weeks? 3 months. Okay, after 6 months, there was much less of a difference, and after a year, there was hardly any difference. So, unfortunately, these diets work for a little while, but then people bounce back. So in the long term, it wasn't helpful. So I suppose if you wanted to lose weight for a particular event, if you had to, a non-sporting event. I tried to do this for a race once, and it was the worst disaster ever. If you want to do anything athletic to lose weight for that, don't ever do this diet. It's horrible. But if you want to fit into a dress or something, like for a wedding, this is the way to go. I've done it for both. And for the dress, it was great. Not this long, but you can lose weight really fast. But it's a long-term thing. It's horrible. I mean, my favorite food is bread, and you can't eat bread. And bakeries were going out of business when this first came out. It was so sad. Bread and pasta, what could be better? So, I mean, if your only concern in life is losing weight, yeah, do this. But if you care about other things, for the planet, horrible. I mean, so much meat, it's not ecologically sustainable, it's terrible. I'm drinking soy milk now. This was not allowed. But if you do need to lose weight for something, for a dress or a wedding, that's the way to go. Okay. So, now this is a really interesting study looking at racial and sexual discrimination. Remember way back at the beginning of the semester, we said there's certain types of things that we want to know about that we couldn't possibly turn into a randomized experiment, like measuring, whether firstborn people have higher IQs than secondborn or something. We can't randomly assign people to be firstborn or secondborn. And we said another thing that we said was exactly this. We said if we wanted to look at, hiring practices, if there's discrimination against blacks or women, we couldn't randomly assign people to be black or white, male or female. And so we really couldn't set it up as a randomized experiment. We'd have to use observational data and control for all the confounders. But guess what? This is an ingenious experiment that is a randomized double-blind experiment investigating racial and sexual discrimination practices. And the way that it's done, let's read about it. It was a really interesting experiment. I think I'm only looking at the racial ones here. Okay, a study investigating racial and sexual employment discrimination randomly assigned common white and common black first names to the same set of resumes and sent them to the exact same set of job openings, real job openings. 5,000 applications were sent in response to 1,300 help wanted ads, and interview request rates were compared. Of course, nobody could actually go to the interviewer to be interviewed because the people only existed on paper. But that was the beauty of it, that you could, if these people only exist on paper, of course you can randomly make them black or white. They don't exist, they're just on paper, and they never went to their interviews. So the only difference that the employers were seeing was whether their name sounded white or black. And what we're looking at is, did that affect how likely they would be to be called back for an interview? Did the white people get called back more than the black people? That's the question. The white sounding names. So let's test it out. So this is a true study. So to test the null hypothesis that there's no racial discrimination in hiring and that the difference in rate was just due to chance, what do you think you would use? Should we do this one as an eye clicker? Get out your eye clickers. You can do this. We haven't been doing eye clickers mostly. Okay, you can't see it up here, but look at your notebooks. You're not seeing it here because I didn't do it, but look at your notebooks. All right, if you want the one sample Z test, you're going to say A. If you think we need a two sample Z test, say B. And if you think we need a T test, say C. The title of the chapter sort of helps you out here, doesn't it? The choices are right in your notebook. It's it's A. Are you on page 247? Yeah, everybody on page 247. It's A, B, and C. 247 is just the one sample, two sample, or T. All right, we almost done. Anybody need more time? We'll stop. Okay, so you're right. It's the two sample Z. Okay. All right, that looks good. While we're here, before we even do this example, let me just show you what your homework looks like. So it was the two sample Z. This is going to be your homework. Remember when you did this survey 4? I asked you, are you in favor of the death penalty for a person convicted of murder? And you either got a picture, this was just next to the picture, this guy I took him from mugshots, or this guy. And so 200, not many people did this survey because I only announced it, I'm sorry. I only put it up for a day. So we had 219 people randomly got the version with this guy, and 323 people randomly got the version with this guy. And everything else was the same. Are you in favor of the death penalty? And here's the results of what you said. You could put strongly favor, favor, unsure, opposed, strongly opposed, and here's the total. Only 542 people total answered this. So what I did was I computed an average. Okay, so it went from strongly favor, you really want to kill the guy, to you really want to save the guy. All right? So my hypothesis was this guy, you wouldn't want to, you'd be more likely, because this guy's scary, you'd be more likely to want to kill this guy than this guy. And it might change your answer of whether or not you're in favor of the death penalty. You didn't know this was this experiment, but I thought it would be fun, and then we could analyze it. So this is your homework. So what I did was I said, okay, here's the data, and for each question, you could answer on a scale of 1 to 5. 1 means you really want the death penalty, 5 means you really want to save the guy. So I thought the people who got the younger guy were going to have a higher average, and they did, because they favored, opposed killing him. But here's your data. Here's the stronger average, okay, bigger average. And so the question is whether this observed difference between the two samples, of 0.318, is small enough that it's likely to be due to the luck of the draw, or if it's too big to be due to chance, it might reflect a real effect due to the images associated with the questions. So you're going to do a significance test. And I explain it here, and you're going to see if that's significant, if that difference is significant. Then I did the same thing. I did it with a bunch of questions with this. So this was, okay, do you strongly favor, it was the same thing, do you strongly favor or oppose gays and lesbians legally being able to marry? And you either had this picture, which I thought was the more attractive couple, or this, which I thought was the more average looking couple. So I thought, you see this couple, you say, oh yeah, I'd like to go to their wedding maybe, I don't know. So I wanted to see if it would affect your answers. So here's your answers again. And again, it went in the direction that I suspected, where I thought that if you got this picture, you'd have a lower number. You'd more strongly favor gay marriage. And I took the average, and certainly it did. And so now you have this difference. And I want to know if that's significant enough. If you think that that is small enough that it could just be due to luck of the draw. Should we vote on these? Let's do the first one. Okay, so how many people think that this picture really changed people's answers, that the p-value is small enough that people do respond differently? It's not just due. So A is yes. Let's start this. A is, well, which question should we answer? Let's see. Do we reject the null? It looks like the difference could just be due to chance, or there's strong evidence that the associated image affects the responses. Which one do you want to vote for? Do you want to say A or B? So rejecting the null means you think that you responded differently because the way the picture looks, and that's B. A is, that difference you saw was just due to chance in your responses. So we're starting it. A is it's just due to chance. B is no, this is going to influence how people respond. Let's see what you think. And then you can do it for homework and you see. So A is no, just due to the luck of the draw. Yeah, it's just chance. You just happen, just happen to get in one group more people who are pro-death penalty than the other. Or did it really have an effect? B is it had an effect. It would influence your response. Okay, everybody voting? There's no right or wrong here. Then you're going to do it. I just want to see what most people think. Okay, everybody voted? Did everybody vote? Okay, so we said A is what? Just due to chance. B is no, it's really going to affect your answers. So you saw B. Okay, you'll see, you'll be able to test it. Let's go to the next one. And the next question Whoops. Okay, so here's the one on gay marriage. So, the people who got this did favor gay marriage more. They did favor it more. But do you think that was just due to the luck of the draw, or do you think the picture really made a difference? We'll go the same way. A is just due to chance. B, no. The pictures would really influence your opinion on this. So A is just due to chance. B is no. The difference is real. It really means that the pictures influenced how you thought. And then we'll see. You'll do it for homework, you'll see. Everybody get a chance to vote? Yeah? Okay, I'm going to stop it. These are just for participation. Okay, so let's see what you said. Oh, you think it was just due to chance. You didn't think the pictures would really influence. Interesting. Okay, so now you can do it. We also did it with the abortion question. We had a fetus, a homely baby, and a cute baby. So we'll look at that one later. Okay, so now let's go back to the document camera. So that's your homework. I'm going to post it right after class. Okay. I'm sorry more of you didn't get a chance to do that survey. That was my fault. It took forever to get those pictures up there. Okay, so you said 2 samples Z. Now let's go ahead and do this problem. So you set up a box model under the null and the alternative. Okay, now the null is always what? That the 2 boxes are the same. The null is always okay, they're always, so in this case, what is it? We have 2 boxes, one with white people, all the white people that apply for jobs, these type of jobs, and all the black people who apply for these types of jobs. And they either get interviews or they don't. They either get interviews or they don't. And what we're saying is that in the general population, these are equal. There's no discrimination of this type going on. It's just in our sample, just due to the luck of the draw, we have some. Okay, so this is what it looks like. All right, and there's millions of people looking for jobs in both. So there's millions of tickets, and what do we happen to do? Millions of tickets. And the null is that they're the same. So we'll say the null is that the percent composition of the box, we can just say the percent of ones, the people who get interviews, is equal in this box, in white box, is equal to the percent of ones in the black box. Among the millions, it's the same. We just happen when we draw 2,500 tickets out of here, and we drew 25 tickets out of here without replacement, because we wanted different people, that we happened to get, what, 10.1% ones here. Wasn't that the difference? The whites were 10, just a little more, they say. And this could easily be due to chance. This is just a little difference. It's not like the whites were the only ones who got interviews. So they say this is just, that's the null. This is in your sample. That's what we got. All right. And what's the alternative say? This is the null, just to set it up. And the alternative is no. The reason we saw this difference, that whites got more interviews, is because they really do in the population. This is not a fluke. This is not a chance occurrence. It reflects the reality of how it is in the population. So that's the alternative. So it says in the real population, the percent of ones is greater here than the percent of ones here in the white box. That's what the alternative says. Can you see this? I'm sorry, it's kind of messy. Okay, that's the setup. Everybody understand it? Now we're ready to do a z-test. The question is this difference, what is this difference? Where are the differences? This difference of 3.4, is that big or small? Well, it looks pretty big. It's about 50% more. But we have to think about it in terms of standard errors. So what do we conclude? Let's go down to here. Leave space, because we have to get some standard errors for percent here, and we've got to get a standard error for percent. And this is going to be the setup. The setup is going to be what? You do the numerator. Tell me what difference you're looking at that you're thinking. Is it big or small? What difference are you looking at? The difference between the two groups. It's observed difference. What difference is it? Does everybody see it's going to be these two differences, this versus that? That's your difference. Is that big or small? That's your observed difference. We don't have to worry about the expected difference, because the expected difference is that there's none under the null. So just think about this is your difference, and we just want to know if that 3.4 difference is big or small, right? But you have to figure out the standard error for the difference. That's the hard part. And you can set it up as you have to combine two standard errors. So it's going to look like that, okay? But you have to figure out these two standard errors here, one for the white and one for the black. So how are we going to do this? Well, standard error for percent is SD of the box. This is 10.1. We'll estimate the box as what? 10.1, which is what? We'll do this. The SD of a box, if it had 10%, would be what? 0.1. This is 10.1, so it looks like that. Times what? How many zeros? Has to be what? It would have been 0.9, but it's going to be a smidgen less, 0.899. That's our SD over the square root of, what do you think I put in here? 2,500. That's n. And then I just have to multiply by 100. Okay? And let's do the same thing here. Now be careful here. 6%. Don't do 0.6. That's 60%. Do 0.0. Move the decimal place twice. 0.067 times 0.9, what? 33, right? Is that correct? That's the SD. Does everybody see that? 6.7 ones and 93.3 zeros in our sample. Questions so far? Now, what's our sample size here? It was the same, times 100. Okay, so we have to do all that out. And I did this out, and I'll tell you what I got. I got 0.6% here, and I got something very similar here. I got 0.5%. So that's what I can put here, 0.6 and 0.5. Okay? The percents are all going to cancel out. So they're going to all cancel out. So now what do I get? 3.4 over, what did I get here? 0.78. And I want to check this 0.78. You know, these are all percents if you want to put them in, but eventually they cancel out, and the z-score is just pure units. All right, now let's look here. Does 0.78 make sense? Is it bigger than either one of these? Yes. But is it smaller than the two added together? Yeah. 1.1 would be the two added together. So that looks right. So now we just have to go 3.4 divided by 0.78. And what do we get? This is equal to, whoops. This is a huge z-score, by the way. Look, if this was a 1, it would be 3.4. It has to be bigger than 3.4. It's 4.35. Hugely significant. So, we certainly reject the null and conclude that yes, there is discrimination here. Because we have to get the p-value. And how do we do that? Do you remember? We just have to place that on the normal curve. Okay, so 0's in the middle. I don't have time to put the discrimination thing. It's so far out, I can't even. I'll just say between 4.35 and negative 4.35. This is overwhelming evidence. 99.9986%. So the chance that you'd see such a big difference if there really was no discrimination is a probability of 0.00, this would be 14, we divide by 2, 0.07. Okay. So, so that was an excellent experiment, and we can, there weren't any confounders, so it was a very ingenious experiment. Now I'm going to ask you like one question. Like, let's go back to the first one. I could have set this up a different way. And this is another way that you can think of it. We chose, let's say, we chose 63 obese people. 63 obese people, all right? And this is the way more or less it was done. You choose the 63 obese people, and you have all their names, you shake them up in a box, and then you randomly choose half of them. In this case, they chose 33 to be in the Atkins, and then you have 30 left in the box. All right? So don't write this down, but you would have, your box model would be, you'd have 63 people, 63 obese, randomly shake them all up, right? This is after they've, and then you take out, well, how many? 33. So that leaves 30 in the box. And these can be your Atkins. And these can be your locale. All right? That's really the way we did it. And each time you did that, you'd get something different. So these were chosen by the luck of the draw. Then you look and you see that the Atkins people lost a lot more weight. They lost, I don't know, 6.8% of their weight, whereas these people only lost 2.7. You still have that same difference. Now, why don't I do it this way? Because when I could do it this way, but it would be a lot more math, and I'd come out with the same example, same numbers you got. Because first of all, I'd have to think, I'm sampling without replacement, and this time, I would have to use that correction factor, because 33 is a big chunk of 63. So that would reduce my standard error. That would bring my standard error down. But then I'd have to think, remember, these formulas only work if you're sampling independently, like we were before. Like when I took these people out, it didn't affect this box. But now, let's say I take out the really motivated people in here. Then it would leave the unmotivated people here. It would make my standard error bigger. So those two things would cancel out. Since I'm sampling a giant amount of the box, my standard error goes down. If I sampled everybody, it would go down to 0. But then it's offset by the fact that if I take out the really good weight loss people here, then I'm leaving the schlumps back here, the ones who are the slackers back here. My standard error is going to spread. And those two things cancel out mathematically through a whole lot of computations, and I guarantee you it works out to the same exact way as pretending that you selected them from a bigger population. And the math works out much cleaner for us, and also has the added advantage of that usually you just don't want to know about those few people. You want to know about everyone who would try this diet. All right? And in fact, the very next example that we do is modeled exactly as a random draw from a wider population of men and women. So we can look at this last problem, and then this one, the model really does directly, the situation really does translate into a beautiful model that's exactly 2 boxes. All right, so why don't we look at this one and think about this one here. All right. Hold up. Okay, so Gallup asked a random sample of 500 men and 500 women if they'd ever fallen in love at first sight. And 36% of the women said yes. And 44% of the men said yes. So I was wondering about this. This was on Valentine's Day. Are men more likely than women to be romantic like that? Are men more romantic and fall in love at first sight? Or is this just chance variation? What do you think? You think men are more romantic? Let's say, so how would we set this up? So this really does translate into this model where you have millions of men. It was a poll. Gallup asked, it was a simple random sample from millions of men and millions of women, and they randomly sampled and it's yes or no. Have you ever fallen in love at first sight? Yes or no? And we don't know what they'd say. We don't know. These are the yeses and these are the nos. Okay? But in our sample of 500, of the men, we got what? Without replacement, what did we get? 44% ones. Well, it's not like everybody does. And here we sampled 500 women without replacement. And here we got only 36% ones. So my question, I was really curious. Does this mean it reflects a real difference in the population? Or could this be due to the luck of the draw? So the null is what? The null is that the 2 boxes have the same percent. The percent of ones in the male box, sounds funny, equals the percent of ones in the female box. And the alternative is what? The reason we saw more here is because men really are more romantic. That in the whole population, the percent of ones in the mailbox, that they really, they just get swept off their feet is really greater than the percent of ones in the female box. So how do we know? I mean, it's not a giant difference. It's not like 90% versus 10%, but I'm still curious. So what would we do? How would we set this up? Do you know? We'd say what? Z equals our difference over some standard error for the difference. And what is our difference? 44 minus what? Help me out here. I feel like I'm just talking to myself. What difference is that? Is that an 8% difference? And then we have to go over the square. Did I do that wrong? I have no notes in front of me, and I'm so tired. So I am very likely to make a mistake, and you get extra credit point if you catch me. All right? All right, what are we going to put in here? What do we have to do? We have to go back up here and do what? Get standard errors for the percent. Ugh, this is annoying, isn't it? This part. So this is going to be the square root of what? 0.44 times what? 56 over the square root of what? 500. And then I have to multiply by what? 100. Whoa. And what am I going to do for this one? This is going to be the square root of what? 0.36 times 0.64 over the square root of 500 times 100%. Yuck. All right, I don't have my, did anybody ever do this one? All right, we got to do this one then. So what do we get? Square root of 0.44, I don't even know if you can see this, times 0.56. What did we get? That looks right. Divided by the square root of what? 500. And then I have to multiply by 100, and I get 2.2%. 2.22%. How about the other one? I'll do 0.36 times 0.64. Let's just make sure that looks good. 0.48. Can you see this? Oh, thanks. Divided by, we went this far, square root of what? 500. Yep. Times 100. Yep. 2.15. Okay. 2.15. Now I'm going to square this one and add it to the other one, which is 2.22 squared, and then take the square root. What, did anybody do that? 3.49%. 3.09, and then I get 8 divided by 3.09. And what'd you get? 2.6? About 2.6? 2.6 is our z-score. What? 2.9? 8 divided by, wait a minute, 8. Why is that funny? 8 divided by 3.9, is that what I even have? 3.09. 3.09 is 2.59. Okay, so this is 3.09, and we get 2.59. 2.59. So what does that tell us? Can you know that's going to tell us to what? Between 2.59 and negative 2.59 is what? It's way out on the charts. It's 2.59 negative, let's say 2.6, where are we? What is that? That's 99%. So this right here is probability is 0.5, a half a percent, Reject null and conclude what? Men are what? Reject null and conclude men fall in love more, conclude men are more what? Romantic? Visual? Men are dogs? What? Women care about deeper things. It takes a while to get to know somebody's character, how hard they work, how much money they have in their bank account. You can't just see that right away. We're deeper. So, reject null and conclude men are more romantic.